This exercise, we're going to deal with the maximum power transfer theorem. Okay, in it, it states that eventually, what would be the best load value for a circuit for maximum power transfer? In other words, if you had some sort of a system, some sort of a circuit here that feeds a load, right? And here's RL. What would be the optimal value for RL based on some of the characteristics your circuit that supplies power has? Well, we know the system that you have here, right, translate to an equivalent circuit. And if we're doing Thevenin, it would translate to something like this: RTH, ETH, and let's say your point A and B are right here. So it's the same thing here. A and B will be right here, and here's your load, RL, okay? And this would be Thevenin equivalent circuit for this system right here. Now, if you did Norton, it will be the same thing. So you will have, let's say, a current source, IN, okay? And you will have RN, and point A and B will be right here, and this is your load vis-a-vis the supplier of power, which is your system right here or your system right here. Now, we've demonstrated in other videos that your internal resistance, RTH or RN, are pretty much the same. So typically RTH will be equal to RN. So we've demonstrated that, so we'll leave it alone. We'll see how that comes into play in terms of determining what will be, again, the best value for RL for maximum power transfer. Okay? Which means if you have values that are below a certain threshold, right, you may not have efficient power transfer. Efficient power transfer means whatever power you generate from here, you want most of it to end up on the load, right? That is the point of feeding your load with some power, right? Current and voltage, right? So you'll have a VL here, right? And you will have an IL here, right? And the product of VL-IL gives you the power against RL. But we know something is going to happen, right? And well, first of all, what is the power at the load? So if you think about this, PL right here, if you're using VL and RL, that would be VL squared over RL. So if you think about that in terms of an equation here of a function of PL versus RL, then it will do something kind of like this, right? So what's going to happen is there is a maxima right here in which you have maximum power. And after that, if you're below a certain point for RL, from here to here, you're not at this point. Or if you're above it, you're not at that point. But no matter where, as long as you're not at this point, your maximum power does not reach this level, or your power is not this max value. We want this max value. We want to be at this point for maximum power transfer. So we want to know what is the RL value that will do that, that will allow us to be here. Now, if this is a function, then we could look at this point here and say, well, what is the tangent at this point? Well, this tangent is horizontal, which means the derivative of this function at that point, right? So d of PL over d of RL will be equal to 0 when you're at this point. Okay? So we're going to use this to figure out what is the relationship of RL vis-a-vis the rest of the circuit, right? So what will be the optimal value for RL for maximum power transfer? So let's start with this equation right here. So PL equal VL squared divided by RL. Okay. let's look at the circuit again furthermore. And let me draw it here. So I have RTH, and I have ETH. Now you could use Norton if you want. And VL is between, or VAB if you want to call it that way, right, will be the voltage drop between these 2 points when you have a load, RL. So we know that VL is basically based on, is related to ETH as a voltage divider rule. So what is that? You know, if you think about it, let's keep this squared. It's ETH times RL divided by RL plus RTH. All of this square. Remember, that's your VL square. And everything divided by RL. Fantastic. So let's open it up some more. So what is that? That is ETH square times RL square divided by RL plus RTH square, everything divided by RL. Well, yeah, so fine, we can get rid of this. So what does that give us? ETH square times RL divided by RL plus RTH squared. Let me just clean up right here. Okay, right there, so we can clearly see the equation. Now, we want to derive. We want this, right? So we want a first order derivative here, or the first derivative, I'm sorry. And what do we have? We have a quotient, right? So what's a generic formula for d of u over v, and this would be dx, right? So what is that? Right, so let's go back to some of your basic mathematics, and that will be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Let me just write these a little clearer here so you can see that's a dv over dx. Over the denominator squared. That's your v squared. Okay, so we're going to apply this rule here. Now, in our case, all of this will be 0, right? So what do we have? Let's look at the denominator. What is that? That's RL plus RTH square. So again, so D, and in our case, PL over D of RL, right? We want this to be equal to 0 eventually. So the numerator, what do we have? We have, the denominator, RL plus RTH square times the derivative of the numerator. What the heck is that? Well, before you do anything, watch this. ETH is a constant. Right? So we know that ETH is a constant. So what does that mean? That means it's it. Since you only have this variable right here, right? So it's ETH square, right? Okay, for that part. Now, let's look at minus. Now, let's put the numerator back, which is ETH square times RL. Make sure you put parentheses here so you can differentiate. Now, you do the derivative of the denominator. What is that? Well, here's the denominator, RL plus RTH square, right? So we know we need to bring that one down, times RL plus RTH 2 to the minus 1, right? So that's 1. So RTH right here. Good. So now the denominator. Well, V squared. Well, that would be RL plus RTH to the 4th. Good. All right. Can we factor out, let's see, ETH squared? The answer is yes. So this is going to be equal to ETH squared times RL plus RTH square minus 2 times RL times RL plus RTH. Everything divided by RL plus RTH to the 4th. Now remember, the key is equals 0. So we want this to be equal to 0. Now, this is going to simplify life a little bit. We know that ETH is a constant, so that's not going to be 0. We're not going to divide by 0, so the denominator is not going to be 0. So what are we left with? We're left with this part that has a good possibility of being 0 for this to be for all of this equation to go to 0, right? So what does that mean? That means RL plus RTH squared minus 2RL times RL plus RTH will be equal to 0. Okay, well, let's open this up a little bit here, right? So that is RL squared plus 2 times RL times RTH plus RTH square minus 2 times RL square, let's see what we can do here, minus 2 times RL RTH equals 0. Okay. So what does that leave us? We could get rid of this and this. And we have RL squared minus 2RL squares. So that's minus RL squared. So that leaves us with RTH square minus RL square equals 0. Well, that's fine. That means now, if you move RL square the other way, RL square equal RTH square. Aha! So what are we observing? That for maximum power transfer, RL has to be equal to RTH, has to be equal to Rn. So this here is your proof to say, okay, what will be the best value for RL for maximum power transfer? Okay, once we've reached this conclusion, then can we find what is the maximum power? The answer is yes. That's not a problem at all. Knowing that what is the power formula again, we could revisit that and find out what is the maximum power now, right? What is this value right here? What is this value right here on the y-axis, right? Okay, we found out the scenario in which we're at that point, but what is that point? Okay, what is its coordinate? Now, we know one of the members is RL going to be equal to RTH is going to be equal to Rn, right? So if you're doing Norton. So now we need to know what is Pmax for that particular point. That particular point, right, has 2 coordinates. It has Pmax and RTH, or Rn, right, as coordinates. So now we need to find the Pmax value. Well, let's go back to the power, right? We've already established that PL, right, was equal to ETH square times RL divided by RL plus RTH, and this was squared, right? Where did that come from? Oh, let me just write it up nicely here. Well, we've already solved that at a certain point, right here. So let me just drive it right here. Okay, now, can we substitute any of the, either with an RTH or an RL? Yeah, you know, your RL here could be either an RN or an RTH. So PL max. Now let's say we're doing Thevenin, right? Which is what we did right here. This was Thevenin. And this here was Norton, right? So if we're doing Thevenin, so PL max is going to be equal to ETH square times RTH divided by, right, RTH plus RTH, right? So if you're looking at it this way, squared, right? So what is that? Right, so that's ETH square times RTH divided by 2 RTH, all of that square. So we could get rid of, we could simplify this. So ETH square, we could get rid of the RTH and RTH here. So we're left with an RTH in the denominator, except we have 4 times RTH. Okay, so if you're doing this in Thevenin, that is what you would get. Now, what if we were doing this in Norton? What is the maximum power right here with Norton? Well, you're going to have a current here that goes through RL. We could do a current divider rule, which will give us our VL that we need, right? So no matter how you slice it, what you're going to end up with, and let me just cut to the chase here for, if you're doing Norton, this is what you're going to end up with. Pmax, or Pload max if you want, will be equal to IN, your Norton current, square, times RN, and the whole thing divided by 4. So I'll leave that for you to demonstrate, okay? Right? So we've done the Thevenin because I spent time on that. So I'm going to leave you to demonstrate this. This will be fun. Remember, you could use current divider rule. You know that VL is still here, right? This current here, let's call it I load. And let me give you a hint. I load is going to be equal to I node or I Norton times RN divided by RN plus RL. So I'm going to leave it there for you to go from here to here. Okay, so on that, I conclude my presentation here, and I hope you go ahead and try this to see if you can get this Pmax based on Norton. That would be a lot of fun if you can do that.